if it's a non-dissipative system, the varying that field will break the symmetry between the two phases. But if it's a dissipative system, their d-dimensional free energy doesn't exist, but the d plus 1 dimensional free energy does exist, but its free energy is a non-analytic function where it can be constant over a range and then take off like one of these e to the minus 1 over x to the n power of non-analytic functions. So,
wait, sorry,
yeah.
a couple questions, Charlie. So, first, why is it so important that the lifetime goes to infinity for larger volumes?
Because if you want, if we're trying to explain why the world is complicated, without, if you're trying to make any kind of a explanation for unbounded complication of the world, you'd like it to have a memory that is unbounded.
And why? And
A stable memory. And so if you make the system larger and larger, you want to be able to hold a thing that is deeper and deeper as you make it bigger and bigger.
I see. But
And if it forgets at a constant rate, no matter how big you make it, it can't do an arbitrarily long computation. It can't even remember arbitrarily long the result of something that you store in it.
That's what the universe does.
What?
that may be, yeah, exactly. That may be how our world is, right?
Well, that's true, but in the whole approach of statistical physics, in the study of phase transitions, is to see the things that happen in finite systems, large finite systems, as understandable by what would happen if the system were infinite.
That just really makes sense, because in statistical physics you have you cannot differentiate in a microstate. You cannot differentiate them in a macro state. You cannot differentiate the microstates, right? But if your system is so large that is bound by constraints, such as the speed of light, then you cannot really make this assumption. Maybe it breaks down the whole idea of statistical mechanics there, right? I mean, you must have some physical properties that prevent you from creating these arbitrarily big systems and then using statistical mechanics on them. Maybe the idea of phase transition is kind of almost local. You talk about long-range order. Well, how long? If you make a change here and it takes 1 million years to go to the other part of your memory, does it make sense?
Well, if you think in that practical way, then you don't care about the difference between stability and metastability. Yeah.
Isn't the 4D toric code only metastable? I mean, the lifetime is growing exponentially in the side of the system, but eventually it will thermalize.
Oh, I mean, any finite system is trivial in the sense that if the
No,
yeah.
I don't necessarily mean that. So if you take something like a two-dimensional classical Ising model,
Yeah.
that actually include local single-site fields,
Yeah.
then the finite temperature Gibbs state really will represent the spins that you directed it, to be all up or something, and it'll never thermalize to the to the negative magnetizations.
What is this at positive temperature? It will thermalize to the Gibbs state that you're pushing it to by the perturbation. Yeah.
Right. Well, and it can be more than a perturbation, and in this case, the Gibbs state really does store that all spins up. Whereas in the toric code, you can't do any such thing, right? You'll be specifically because it's a topological code. So that's why I would say the toric code is metastable, whereas this 2D Ising model with local fields really has its thermal state represent.
Well, but I think that the toric code examples will give you. I won't say that if you just cooled the system, it would go into one of the toric code memory states. But if you put it in that state,
Yeah.
the lifetime of the state would increase as you made the system larger, which
I agree.
the ordinary Ising model won't do.
Okay, but the
Yeah.
the Ising model will do, right?
Well, I think you're talking across purposes whether you imagine that you have control of the Hamiltonian or not. You're imagining you do, so you can set the magnetic field.
Yeah.
Oh, no, I'm saying,
You're saying you'll give it, someone else gives you the Hamiltonian, and can you store the information in the state, given that Hamiltonian?
that's right, that's right, yeah.
I'm talking about that too.
Oh.
And so in this example, though, you have the actual Gibbs state of the 2D isomodal with the local fields really is concentrated on these all spins up magnetization.
Well, that's right, but that's bad, because it means if doesn't work as a stable memory because it has only one stable state instead of two.
Okay.
And if an Ising model in zero field is bistable as if
Sure.
below the Curie temperature, but if you put on any little field, then its lifetime is independent of the size of the system.
Sure,
But with these dissipative models like the Tomb model, or with the toric code, you can get the thing to be have a lifetime that increases with the size of the system, which I says is my criterion for stable versus metastable memory, although maybe other people use those words differently.
well, it's not the Gibbs state, is it? The Gibbs state doesn't store, but.
No, the Gibbs state, but there are other states that do. Yeah,
Okay.
yeah, that's what I meant. Yeah,
As well.
that's right. Yeah, and I think that's an important distinction, because if we think cosmologically, to have a stable memory, it's a special, hard to prepare state, and yes, it will last forever in an infinite system. But the infinite system is not going to, or a large finite system is not going to go to that state. And if we are inhabitants of that universe, it would be very lucky for us to ever find ourselves there. So that's a little discouraging from the point of view of explaining why the world is complicated. So that's the questions I have in terms of relation of stable memory to where complicated states come from, and if they can still exist in the systems that equilibrate. Now we're going to go on and talk about, this is an idea of which goes by the name of quantum Darwinism, which is invented by people like Wojciech Zurab and Robin Blum-Cahood. But this is the idea that a version of decoherence theory that says that when you have a system that interacts with a lot of environments, sub-environments that don't interact with each other, then this is one of the things that, and Jess has explored this in much greater detail, gives rise to Ein selection, to a preferred basis, so that the system is correlated with it's correlated with each of the sub-environments in a preferred basis, but in another basis, it's in any other basis, it's only correlated with all of them. It's an outcome of entanglement monogamy. Wait, what happened here? Is it okay? So this is the common example of this is the fact that the illumination of all of us by photons, some of which escape, essentially will put us into a mixture of eigenstates of position. But if you trapped all those photons like I did in my reflective box and let them come back and be reabsorbed many times, we would lose our classicality as well as losing our complexity. So as I said, when the system runs a long time, the evidence that it had that history is obfuscated. It's not there anymore. But conversely, a deep structure, one that seems to have had a complicated history, could have come from a much shorter and more trivial history. And this is the Boltzmann brain phenomenon. And this was suggested to Boltzmann by a friend, and he mentioned it in one of his papers, that the low entropy world that we see is due to, this was of course written before there was an understanding of expansion of the universe, that maybe the world is infinite and at equilibrium, the universe. This is a very old-fashioned 20th century, early 20th century idea. and that we're just, it's so big that we happen to be in a fluctuation, and we find ourselves in that fluctuation just because if we're in one of the more boring parts of the universe, we wouldn't be complaining about it. But then this idea was found out to be too strong as an explanation of our world, because the most likely fluctuations would be ones which are just small enough to support a temporarily existing brain. So in the Boltzmann type of world, a world at thermal equilibrium, the most likely fluctuation that gives me the perception of being in this room lecturing to all of you is one in which the rest of the room and the rest of the world is at thermal equilibrium, but a temporary fluctuation has produced in my mind the illusion of being 75 years old and having read all these books about cosmology, and so all that is an illusion. So these illusions occur much more commonly along the dynamical orbit of a unitarily evolving system, or the orbit of my little cellular automaton. If you say in that system, say, let's look at this. Go back to here. Yeah. So some particular acute thing, like say a pattern of that sort. Anytime a pattern of that sort arises, it will say from the logical depth point of view, what's the most plausible origin of this in terms of a universal computation? Well, the answer is probably this one here. But if you said, if the dynamics of this system is what it is, and we don't know where we are along the trajectory, this local pattern could have originated with any other garbage in the rest of it. So we have this kind of tension that I don't know how to resolve between assessing the plausibility of a configuration according to how likely it could be produced by a simple description by a small amount of computation, or maybe a large amount of computation, and assessing its probability in a statistical mechanical ensemble that comes from our knowledge of the dynamics. So I think that's a problem I'm still grappling with. How should we judge plausibility? Should we judge it, as I've been doing, according to this algorithmic information way of thinking, according to the universal semi-measure, or which is the mathematization of Occam's razor, or should we say we are like the inhabitants of the Borges's Library of Babel, where the people lived in a very large library in which all possible books were written, except that they were all jumbled up so that you can't learn anything by looking at the books. So I don't have the answer to that question, and I hope somebody does.
Well, you're in a worse situation than you think, because the most probable fluctuation of a Boltzmann brain is one that's just smart enough to understand the problem of a Boltzmann brain, but not smart enough to solve it.
Yeah, that's. I think you've hit the nail on the head there. Yes. Okay, so where were we here? Thank you. So this was brought to my mind from reading. So now you see what the Boltzmann brain problem is. When the heat death of the universe was discovered in the 19th century, people said, oh, well, we don't have to worry about that for a long time. And maybe that's the attitude of people now. But unless you want to say something that is a priori arbitrary, that is, I live in a world governed by these laws, and for no particular reason, I'm right near the Big Bang, rather than at some later time. And then, but our understanding or our experience, for example, if I go and open this door, and I say, I'm going to test whether I'm a Boltzmann brain or not, because if I'm a Boltzmann brain and open up this door, and there's another door on the other side, that says D, well, that's evidence that I really live in an ordered world. But that actually is a faulty argument, because my memory of just having done that probably came not from just having done it, but from a fluctuation in my brain that says I went there and looked outside. So there's no direct way out of this conundrum of saying you have to assume that you're at a special point along the dynamical trajectory. Yes?
So Mark Strednicki and Jim Hartle have this sort of philosophy of science, but they say that where you are in the universe should be part of your theory. And that you should not say, I have my observations, I have an external world, and then I am forced to, by self-consistency or something like this, to pick amongst those randomly. They say, listen, my theory of the world says I am 13 billion years after the Big Bang, and that's just what the theory is, and it works, and I can predict things with it.
So I want to up the ante a little bit on that. So I think almost the same thing as those guys, which means they and I argue all the time.
Yeah.
But as usual. But I'd say you're using this heuristic idea of how you place yourself in a universe where there's many places
Yeah.
might be